Assalamu alaikum. In this lab session, in this video, the instructions for the lab session number 15 will be made, and the proposed statement for the lab session is shown here. To create translational multi MDOF vibratory system, means multi degrees of freedom vibratory system, and simulate all their modes and verify their natural frequencies. So here, as a reference, example 5.1 from the textbook of mechanical vibrations by S.S. Rao will be used. Frequencies of a spring mass system, and here is shown the statement. Find the natural frequencies and modes of a mass spring system as shown in figure 5.6. So here we can observe the figure 5.6. Here is shown the schematic for a two degree of freedom system. So for the multi-degree of freedom system, so we can extend this methodology for multiple masses more than 2. So here we can also observe that here are actually shown 3 springs, because third spring is actually auxiliary springs, and only 2 springs can work sufficient. For example, K1 and K2 are sufficient, and this K3 is actually just an assistive or supporting springs. So it is actually not influencing the DOF of the 2DOF system. So as he can observe here, mass M1 and M2 have been made equal, and all stiffnesses have also been made equal, because here in the statement shown that N is equal to 1. So stiffnesses for all 3 springs are same, and the masses for both the point masses are same. So we will be first creating the geometry for the system. So we will be launching a model module, and we will be clicking on geometry cell. And design modeler will be loaded, and after that we will be creating selecting the XY plane and go to sketching tab. We will be clicking on Z-axis, and here we can, for example, randomly create 2 masses. So we can arbitrarily draw 2 rectangles about this y-axis at some approximate locations, and after that we will be making dimensions to specify their locations. So here we can observe that we can use the vertical dimension between this line and this line. Is 6, so we can make it actually 1, so that the length for the each spring, it can be assumed to be 1 meter, for example. So the length for the each spring is 1 meter, and the dimensions for these cube will now be made. So we can use some symmetries. For example, we can click on constant and make a symmetry, and we make these rectangles symmetric about vertical axis. So click on y-axis, and then click on this point and click on this point. So this rectangle has been made symmetric. In a similar manner, click on this point and click on this point. So this rectangle is also been made symmetric. After that, we will be inputting the vertical distance between this first mass and this second mass. This distance must also be 1, as the spring will be placed between them, and its length will also be 1. And now we can create the dimensions for these rectangles. to make them simply squares. So what we can do, we can apply a equal length constant, and we can make this length equal to this length, and in a similar manner we can make them also equal. And after that we will be making same dimensions. So for example, we can further apply a further constant a of equal length, that we can make this length equal to this length. So in this way identical lengths or dimensions have been made. And furthermore we can constant one side as to be, for example, this side length is actually for example, we can make it to be, for example, 1 meter, for example, that is sufficient unit mass. So in this way, two masses have been created. We can further move the dimensions a bit closer so that a better view has been shown. So in this way, the sketches for the masses have been made, and after that we will be selecting this sketch and we will put in 3D mode, and then we will be extruding these two rectangles and these two squares, and we will be clicking on apply, and we will be uh, x direction will be both symmetric, and we can take it to be extrusion depth to be 0.5 meters, so that simple cubes are made, each having dimension of 1 by 1 by 1. So so unit cubes have been created for two masses. So here we can observe that the volume for each cube is actually 1 meter cube. So if display we make display planes off, then we can observe from the z-axis that the two masses have been created like this, and in the 3D mode they have been shown here. And now we will be uh, clicking on this model cell A4, and we will be waiting for the design modeler, sorry, the model cell to load. And once it has been loaded, further analysis will be kept continued. So as the model have been imported, here we can observe the properties of the solid. And for example, here we can observe that the mass is actually 7850 actually, because the volume is 1 meter cube. So if for example we are required unit mass, for example, because both masses are equal, so we can take unit mass. So it means the density must also be 1, because the density is mass per unit volume. So if we can assume the mass to be 1 kilogram, the volume is already 1 kilogram. So 1 by 1, so that means the density that we can input here in the engineering data simply 1. And then we can simply refresh materials, and then we can observe that the mass for each body is 1 kilogram. So masses have been made 1 kilogram, and after that we will be applying spring. So springs will be applied, and uh, we can observe, for example, the stiffness for every spring. For example, 1000 Newton, we can simply assume that the stiffness for and for this third spring, for example, we will apply first of all third spring, and this is a ground and this is a mobile body. So this will be used as the reference body and this will be used as the mobile body. So here we will be inputting in the scope as body dash ground, and in the reference in the mobile uh, we will be clicking on the scope, and then we will be a bit rotating so that this lower face has been shown here, and after that we will be input will be clicking on this face so that, and this face has been shown here, and after that we can observe that a spring has been installed in the lower face here, and now we will be making its length. So here we can observe that its mobile coordinate is y. So uh, we can here if we want the length of the spring to be 1 meter, then we can observe here that the reference is, for example, on x-axis or on the origin, so it is 0 already. So in this way spring of length 1 meter has been shown here, as we can observe. So after that we will be adding another spring. Click on insert spring for, and then we will be making the second spring, and we can assume the same stiffness, for example. So, and because the second spring will be made between mass m1 and m2, so this will be, because both are actually mobile bodies, so we will be using scope as body dash body. So here we will be using body dash body as default has been shown, and now in the reference or in the mobile. So remember that both of these bodies can be alternatively made, the reference and the mobile bodies. So for example, we can click scope in the reference to be, for example, this face of the body. So after that we will be clicking in the mobile, for example, this lower face, so we can a bit rotate here like this, and so click on here, so this face. So in this way the spring will be placed centrally above these two faces. So after that we will be placing the third spring. So the third spring here, as shown, that the third spring will be between the ground and this mobile body M1. So that will be placed here like this, that we will be clicking at, for example, its stiffness is also 1000 Newton meter, because the stiffnesses were assumed to be same. And in the mobile, we will be clicking on scope and on this face, for example. And after that, we will be calculating the coordinate for this upper point. So here this point was at origin. So we can observe if the length of the string to be 1 meter. So its reference coordinate will be here. So we can calculate here the y coordinate for the reference. So this is 1. So the side of this cube is also 1, so this spring is also has length 1. So 1 plus 1 2 plus 1 3 plus 1 4 and plus 1 5. So that means we will be inputting y coordinate to be 6, because 1 2 3 4 5, sorry. So we will be inputting the y coordinate in the reference. uh, First of all, we can select here body dash ground. So now we can input as it to be 5 meter. So as we can observe that the all three springs have been shown here. So in this way, shaded exterior, if we put, so all three springs have been placed, and now we will be applying actually remote displacement, so that these sub, two bodies are made to move vertically downwards. So to constant their DOF, so we will be applying a remote displacement individually. For example, first of all, we can apply a remote displacement at, for example, at this face. So we will be clicking on this face, and this face will be moved vertically down, because all both meshes move vertically down. So we will be making x0 and linear y free and z also 0. Only y may be made free, and rotation about x will also be made 0, and rotation about y may also be 0, and rotation about z will also be 0. And after that, we will be clicking on rigid. So in this way, remote displacement, and after that we will all be clicking on remote displacement again, and another remote displacement will be made at this face of the body. We can observe that any of the four faces, side faces, can be made as the remote face. So we will making x free and y z also z also to be free, and rotation about x must also be free, and rotation about y must also be 0, and rotation about z must also be 0. So only linear translation along y is free, and all other parameters or coordinates are 0. And here we will be behaving, setting its behavior to be rigid. In the analysis setting, because this is a 2DF system, so we will be applying here two modes. So after that, we will be inserting and deformation and total deformation. And now we will be solving, and we will be observing its frequency, and then we will be verifying from the theoretical formulas. So here, as we can observe that the two frequencies are shown here, 5.033 and 8.717. So we can, for example, uh, create a mode shape result for the first mode, and in a similar manner we can create the mode shape result for the second mode in this way. So once again solving, we can evaluate our results here, and this is the first mode and this is the second mode. So we can rename them to be, for example, this is first mode and this is actually the second mode. So second mode. So as uh, we can oscillate in the first mode, we can observe here in this way both the masses are moving upwards in the same orientation. And in the, if we oscillate the second mode, we can observe that both masses are moving in the opposite orientations. So from the sidewise view, they can be shown here. And now we will be verifying the modal frequencies in hertz. So the formula for the modal frequencies which has been calculated here, omega 1 and omega 2, here they are shown on that omega 1 is k by m. So omega 1 is for the first mode, so we can calculate that the K stiffness was 1000. So mass was actually unit. So we can take its square root. It is 31.62. And then we will be dividing it by 2 pi so that the linear frequency has been calculated. So as we can observe, our answer is 5.0329. And here the answer shown is 5.033. So this frequency has been verified. And now let us verify the second frequency. The second formula for the second frequency is 3k by m. So that means we will be multiplying 1000 multiplied by 3000, and the mass is unit. So we can take its square root. This comes out to be 54.7722. And then this is actually the circular frequency, omega 2. We can divide it by 2 and pi, then this comes out to be 8.7172. And here we can observe that the answer is 7.713. So these have been 100% verified. So thanks all for listening and tolerating. Jazakallah. Assalamu alaikum.